Okay, so let us start with today's topic. So the topic is complex differentiation. I believe this is the fifth class in that. Complex differentiation. So first of all, let us mention a short-term goal for this. Then it will help us to understand why we are doing what we are doing. Okay. So the goal, short-term goal is to be able to decide, right? Decide a complex function, when a complex function f, so it could be from C to C, but essentially we only need the range to be C. The domain could be a subset of C, so it could be something which is a subset of C. And we have talked about this earlier, that this should be an open subset usually, and oops, sorry. Yes, the goal of this is to understand when a complex function from C to C is complex differentiable. Okay. Now, why is this question even there in the picture? Why are we even asking this question? Right? Why is it not? Because complex differentiation is new. Okay. This thing, complex differentiation is a new thing. In what sense do I mean this? I mean, if you look at the very definition, okay, let's look at it. Let's look at the definition. F is let's f is complex different. Let's call it CD at a point z naught. If we have this is a somewhat complicated limit, and this is limit h going to 0, and h is a complex number. So h going to 0 means when the complex number goes to 0 means that its modulus is is going to 0. Limit h tend to 0, f of z naught plus h. Obviously, we had derived other many useful equivalent criteria which we'll use, but for the time being, it is just this. If this limit exists, okay. Now, it is usually not easy to directly decide, or to, without any theorem or something, to directly compute this limit or know if this exists or not. Okay. Because in this, you can see that the h can change in many ways. The h can approach 0. So h could be something like, ix, where x is real, and x goes to 0. Those values will also be, so when it is approaching along the real, sorry, then it will just be x. Ix means approaching along the imaginary. But this is not it. It could approach in many different ways. Okay. So really, to calculate this limit is a tough task, usually. It's not very straightforward. So we want to calculate this limit, and also, more importantly, decide if the limit exists by using real differentiability. That is really what we are trying to do. So maybe that's what I should add here. Differentiable by using, and this is just the philosophy that we want to use the previous simpler thing to really do the, by using real differentiability, right? That's what we want to do. Also, one must mention here that is a new thing and it's a very strong property. Now we'll do an example for this. It's a very strong property, meaning that something being complex differentiable is a much rarer event than it being real differentiable. Okay. Let us see that through an example. So I'll remove the definition, so we don't need the definition too much. We know this. So first, let us compare with real differentiability. Real differentiability. What do I even mean by real differentiability here? Well, this function that is from C to C, the function f that is from C to C, or from a subset of C to C. Here, this f can be viewed as function from R2 to R2, or a function from a subset of R2 to R2, right? Simply put, we have already seen this thing. So simply put, f is essentially x, this x plus iy. We can instead just write this as, just 1 second. We can instead just write it like this. And then it just becomes 2. So, I mean, this at every input, you'll have a real part and imaginary part. So essentially, it is 2 functions. It is 2 functions from R2 to R. Okay. A complex function is just 2 functions from R2 to R. And what I meant by comparing with real differentiability, or rather using real differentiability, is that we want to see the differentiability of this and be able to comment on the differentiability of f. Okay, but first let us see that it is not such an easy connection, is not trivial. That, I mean, we cannot say that if u is differentiable and v is differentiable, then f will also be differentiable. No, that is not true. That will not be true. And that's the example we want to see. Okay, so let us just do the example here on the side. So this is a very standard example, fz equal to z bar. And standard example, and this is like the only example in the sense that we will see it later. Like if a function doesn't have a z bar, then it is complex differentiable. That is also somewhat true in some sense, but we will see. Let's take this function. So we know that it is not complex differentiable, that we have seen, and that is easy to check. Not. Okay, right. So what we'll try to do is we will replace not complex differentiable by holomorphic now. Okay, is not. That is the same word we know. And is not holomorphic at what point? So what was the point? I mean, it is not holomorphic at any point. I think that is, let's just check it. I think that is true, but let us just check it. So if you just do f of z plus h minus f of z divided by h, then you get this. Yeah, this limit does not exist. So you see, it is not holomorphic at any point. At any point. Not holomorphic at any point. It's not like it is not holomorphic at one point. No, it is not holomorphic at any point. Okay, that is, and we have shown that as h goes to 0, this limit does not exist, because if you tend along the reals, you get something else. If you tend along the imaginary, you get something else. So that we have already seen. Yes. So analytic function a priori, there is a difference. A priori analytic function means that if you pick a point in the domain. Okay, so f is analytic. F is analytic means that if you pick a point x naught in the domain, okay, then around a neighborhood of that point, around a neighborhood of so x naught could be in R2, or you could take it in R, whatever. Then there will be a neighborhood around it such that f will be equal to a power series. F will be equal to an infinite polynomial in some sense. Okay, so f will be equal to something like this: a1 x minus x naught square and sort. So f will have an expression of this form, and this will be true for all x, in a neighborhood around x naught. So not everywhere in the domain. Okay, so given a point in the domain, there will be a small place around it such that there it will look like a power series. Very simple. This is a very simple function. Obviously, when you change the point, then this power series will change. Okay, so that is there are some delicate aspects to that. Obviously, what does this even mean? Basically, it means that if you take if you consider this power series first as a starting as a sequence, as a series, and you take the limit and tend to infinity, then that limit is equal to the function f. So that is what analytic function means. A priori, that is a difference. And you can obviously see that an analytic function will be infinitely differentiable, right? It will be infinitely differentiable. But complex differentiability doesn't mean analytic to start with, but later on, we will see that they are the same things. And that is quite magical in some sense. So it means that if a function is differentiable once, if it's complex differentiable once, then it is complex differentiable infinitely many times. And more than that, it can be written like a power series. It can be written like an infinite polynomial. So those are some magical things. I do not have a clear intuition for why those things happen. A bit mysterious to me, but they happen. Okay, maybe when I explain, maybe it will be clear to me also later on. We'll prove this result later, but it will come a little later. It's not easy to prove. It's not. Yeah, it's not easy. Yeah, but I can give some intuition, but that will not be very useful now. Right. So let us come to this easier thing right now. Is this is not holomorphic at any point? We know this, but if we look at it, we want to look at it. See, our goal currently, the local goal is locally we want to compare real differentiability with complex differentiability, right? This is not complex differentiable, but we can try to understand if it is real differentiable or not. So first of all, what is it as a real function? What is it? What is this function f as a function from R2 to R, R2 to R2? Right? It is really just two functions, right? X comma minus y. That's what this is, right? So the ux comma y part is just x, right? And the imaginary part is just minus y. This is where the problem already has started. The real part and the imaginary part are quite unrelated to each other. And this is the fundamental reason why this is not differentiable. Okay. But in any case, we know that it is not complex differentiable. But then the question is it real differentiable? Okay. So we have this function and we are asking, is this real differentiable? Is f real differentiable? So just think about this. Is it real? Should it be real differentiable or not? And what should be its derivative? Right. So we are basically asking, if this function is real differentiable, and so there are two functions, right? We have covered real differentiability of functions from R2 to R, and there are two of them here, right? And we just want to check if both of them are real differentiable or not. Well, it is obviously that they are. But to actually write a proof, well, you can use one of the conditions. So we had said that if you remember, if you have a function from R2 to R, which is basically two variable function, okay, giving a one variable output, if you have a u, okay, and if the derivative with respect to x and the derivative with respect to y exist and continuous. So continuous was important, okay. The partial derivative existing is one thing. That doesn't imply differentiability. Differentiability of this R2 to R, what does it mean? Let's just quickly review that. So if you want this to be differentiable at a point, let's say x naught comma y naught, then it's basically this. It is this minus at the point minus there should be a vector. There should be a row. There should be a vector, right? A vector in R2. There should exist a vector there, and well, we know what that should be. We have already checked that. But in any case, once again, sorry. Array. We know that there should be something here, and well, that's something we can later find out. Later, we found out that it should be just this, such that this times this mod of this goes to 0, but more than that, even when it's divided by h, it still goes to 0. This is the condition, right? This is a very complicated looking definition, but if you really think about it, this was the most natural definition, right? Because we wanted it to capture we wanted to know the equation of a plane of a surface at a point, and then we needed these two things, and we kind of motivated it. So this was the definition, right? And then we found the condition that if these two partial derivatives exist and are continuous, then this will go to 0. This will be real differentiable. And obviously for this it is true, right? Because this, in our case, this is equal to 1 and this is equal to 0. And obviously those two functions are constants, so they are continuous. And so this is differentiable, right? So this is differentiable, and this is similarly, this will also be differentiable. And so this is also differentiable, right? And so yes, it is real differentiable. Okay, it is real differentiable. So maybe this is something that we can remove. Yeah, but one has to, at the beginning stages, that really has to check those things. Okay, it may look very obvious that it is, but one should check it. So yeah, this function is real differentiable. Okay, but it is in fact more than that. That's what we want to see. So we have already seen that it is real differentiable but not complex differentiable. But we want to see more than that. Let us try to understand what this is. So this is what the way we are looking at this. This is a function from R2 to R2, right? It is a function from R2 to R2. If we want to understand where this function, what this function does, right? That is what we want to understand, right? Well, if you take a vector, then what will this function do? This will or a point in R2, this will basically send this pointer to this place. It is just reflection. This function is just obviously we obviously know that it is reflection about the real line. That is what it is. And more than that, or rather, that special case of that means that if you consider this kind of function, it has these very interesting properties. Right? Take this, then becomes this. Means that basically if you want to reflect a sum of two things, then you can first reflect those things, and then you can take the sum of the reflected parts. That's what this means. Right? See, this is the property that this function shares. This function has. So this is what is known as a linear function. Okay? This is a function. This function, if you look at this function, it is what is known as a linear function. So let us see what that means. That means something very interesting. If I remove all this and just write this, then you will understand easy also. So basically what I'm saying is that if you take two vectors now, if v1 and v2 are two vectors in R2, then this is what is satisfied. And this is again very obvious, as I just said, right? You take two vectors, you first add them and then reflect, or you reflect them and then add, it doesn't matter. You'll in the end end up in the same place. Even for rotation, same thing happens. Right? Well, this means that this kind of function, okay, let us look at what happens to this. Right? This point is just fixed. Right? This point is just going to this point itself. And let us look at where this point goes. Means this is the first vector, right? The first unit vector. And this is a unit vector along the y direction. And what happens to that? That just becomes this. Why are we calculating these two values? Because this is all we need. This is all we need, right? If you now want to calculate f of, let's say, 3, 5, then what can you do? You can break it up like this. Just doing it in one step. It's very easy to see that it's true. You see, you can just do this. Right? So what my point is that whenever a function satisfies this kind of property, then you only need to know what it does to the unit vectors, one on the x-axis and one on the y-axis. And if there's a third dimension, then one there. For a function like this, you only need to know these things. Right? You don't need to know all the values, all the input outputs and so on. You just need to know two things to determine the function, where 1, 0 goes to and where 0, 1 goes to. That's all you need to know. Right? Right. And then what does that mean? This means that this function can be represented as a matrix itself. So you can also read this as a matrix. Okay. And obviously this this f of 1, 0 here is 1, 0. So you can write that like this, and this 0, 1 you can write like this. So in the end, what do we get? In the end, we get that this function f, right? This function f from R2 to R2 is nothing but a vector getting vector v1, v2 maybe. It's just, so here it means maybe I should just say x1, x2. x1, x2 going to this. Obviously, we know that it is x1 minus x2. or x comma y maybe, since I already used that notation. Sorry. So we can use that notation itself. Right. You see, but the point here is that this kind of function, which has this property that you can, before adding it, you can first evaluate and then add. You can understand. It's called linearity condition. Obviously, you see this in Olympiad questions also. From R to R, a lot of places you see this kind of conditions, and other conditions can be transformed to this and so on. But the point being here that this kind of function can always be looked at as nothing but just the multiplication by a matrix. This kind of function can always be looked at in this way. Okay, because that's what you demonstrated here, right? Any value, suppose 3 comma 5 you want to calculate, you can just do it like this, and this is nothing but this matrix multiplication, right? So this function is simply this. It is just, that's what it is. Any linear function is like this. So now let us use this to not just prove the derivative, but also find the derivative of f of x comma y of this function f. Okay. Obviously, we have already found the derivative in another way, but I want to just make another point. Let us see that. Let us replace this thing, or let us just replace this thing completely and look at something more cleaner. Just a very dummy example to start with, okay? If f is a function from R to R and fx is equal to some c times x, right? Then what is f dashed? What is the derivative of f? The derivative of f is just the c. It is just that multiplication factor. Everybody knows this. Now, if f is a function from R2 to R2, I mean, I think it's important to just get an intuition for real differentiability. This will help us, in complex differentiability, and this should precede it. But in any case, it doesn't matter. If f is from R2 to R2, such that f of v1 plus v2 is equal to this for any vectors v1 and v2, and f of constant times v1 is equal to constant times f of v1. Okay, for any v1, for any vector. If these things happen, then we have seen that f can be written, f is nothing but, or rather I should say, f of v is nothing but a matrix. We can understand what those things are later. These things can be figured out, but f will look like a matrix. F will look like a matrix multiplied by this vector v. This is a vector, it has two components. You can write it as a column. Okay. You see, so we prove here, if we have this condition, and this condition, right, then this, you can use this to prove this, right? I'm just saying that this case from R2 to R2 is nothing different. If again you have this scaling condition and linearity condition, then also you can write f as a multiplication by a matrix. It's very easy to, again, we should actually try to write this out, maybe try to write it out in general, like just for this, not just for the example we did, but for this. So again, you have to calculate f of 1 comma 0, assume some value for it. You will not know a value because you don't know what actually the function is, but those values will feature in the matrix, and those values will determine all other output values. Okay, basically these kind of functions are determined by only two images. Okay, this is what it is, right? So very simple. We want to understand what is the derivative of f. What is derivative? In the real case, we saw that the derivative was just a constant. Okay. In the real case, we saw that the derivative was just a constant. We want to understand what is the derivative in this case. Okay. So if you now have a function from R2 to R2, then how should you define the derivative for it? Well, it is just the same concept here. If you take a general function f from R2 to R2, so if f is from R2 to R2, then how do you define its derivative? You can define it to be the derivative. You can take the derivative of the first part and the second part. There are two functions in this, right? R2 to R, there are two functions. You can say that, you can use that, or you can simply, let's say you're trying to calculate the derivative at a point v. V is just the vector now. I'm not writing v1 comma v2 plus h minus f of v minus, now what should we put here? So here we were using a row vector. Right? Now we will use a matrix, because you can see that is the only thing that fits in. Okay, because this is a vector in R2, this is a vector in R2. So you want a matrix and you want a h. So this will be a matrix, 2 by 2 matrix, and you want a h, which will just the h, but I'm just writing it as h1 comma h2 maybe. What will this matrix be? Once again, if you just do the same kind of things that we did earlier, you will see that the matrix will be the derivative. So f will be two parts, right? f1 comma f2 or u comma v, two real functions from R2 to R. So it will just be take the derivative of f1 with respect to x, take the derivative of f1 with respect to y, take the derivative of f2 with respect to x, and take the derivative of f2 with respect to y. That's what it will be. So basically, if you can just find some matrix there which does it, then that's it. If you basically, you have to just, given f, if you can just guess a matrix which will make this limit 0, then that's it. That's all, right? Because we know that there's only one such matrix that will work. The derivative is unique. Let us see what it will be in our case. Okay, in our case, we know that f of v plus h just means that f of v is just this, because that's what we have already proved. That's a good thing we have proved. Now we will use that. If we calculate f of v plus h, it is nothing but, well, I mean, we can say it's easily. We don't even need the matrix. We know that we can say that this is just f of h. Is that right? This we already know, right? It is just f of h. So this difference is just f of h, and that is a good thing. I mean, it's already a linear function. Okay, so it is just f of h, and so we are having sum a, b, c, d times h. Now you want to pick a matrix, some matrix you want to choose, such that this limit divided by this limit goes to 0. What matrix should you choose? Obviously, we should choose this. There is literally no other possibility. This is just in front of us, right? So we just choose that. And so the matrix, which is also the derivative, which is also a matrix, is nothing but the same thing. So the derivative is the derivative which is a matrix, or if you want to look at two derivatives, derivative of f1 and derivative of f2, then well, the derivative of f1 will again just be f1 itself, and the derivative of f2 will be f2 itself. So in short, the derivative df will just be, the derivative is a function, right? The derivative is again a matrix, which is a function, but it's just a matrix to start with. Whatever. So this matrix is again this. So if the function was given by this matrix, the derivative is also the matrix. This is exactly what was happening in R2R case. Obviously, there the matrix was 1 by 1. Right? So we have proved something very interesting. We have proved that, okay, why are we doing it in this context? I will say, but we have proved that the derivative of this function is again the same thing, the same matrix again, which means it's again the same function. And so this will again be differentiable. The derivative as a function from R2 to R2, because the derivative is this derivative, which is ABCD, this is also a function from R2 to R2. You can plug in a vector and you can get a vector out as output. But it's the same function, right? So the derivative is the same function, so you can take differentiation again, and the derivative will again be, if you look at the derivative as a function, in the real case, we look at the derivative as a number. Obviously, the number c can also be looked at as a function. But any case, anyway, the point here is that it becomes infinitely differentiable. That was my point. It is infinitely differentiable. The derivatives are themselves. Okay. So is that okay? Right. Okay. So then this is the case, and f is infinitely differentiable, and f is infinitely differentiable. These functions are very interesting. We will see them. We can use them for rotations and many other things. Yeah. So this function is infinitely differentiable, but not at least z going to z bar, which was x comma y going to x comma minus y. At least that. Some of them, like rotation, will be differentiable, will be complex differentiable also. So not all, but this particular f, which is infinitely differentiable, is not complex differentiable. So you see, we have an example of function which is infinitely differentiable, but it is not complex differentiable. Okay, so complex differentiability is a much more stronger thing. Okay, and that's why it is difficult to decide when it is. I mean, it's easy to decide when it is not. That is easy to decide, but it's hard to decide when it is. And that's what we are looking for. And yeah, so let's keep going in that direction. So let's clear this. And so we have looked at the goal, we have looked at real differentiability, we have compared it. Now we want to see if we want to understand, yeah, that is I think what we want to now do. We want to relate, because as we said, the goal was to be able to give condition to decide when a function is complex differentiable in terms of real differentiability. So we need to be able to relate, right? We need to be able to relate real and complex differentiability. So that is what we will do. Well, so what do we know? Real and complex. We want to relate these things. This is just a natural thing to do. If we just do this ourselves, we can get the necessary conditions for complex differentiability. And then one can try to prove that they are sufficient, maybe with some more conditions, which one can figure out along the way of trying to prove converse. But anyways, let's get to this. Let's see this just once again. Just write the definition clearly. Then we can just compare them side by side. So f is a function which is from R2 to R2. Okay. If you want to think, you can think of it f like this. Two pieces. What does it mean for f to be differentiable? At a point, it means that this minus this minus there must exist a 2 by 2 matrix. It's basically two row vectors, one for the f1 and another for the f2. Okay, because this f itself is f1, it's f1 comma f2. Yeah, but I'm just clubbing it and writing it in one. That's why it's a 2 by 2 matrix. But we want to really see that because in the complex differentiability, which is what really we're interested in, the real and the complex differentiations are, or I'm sorry, the first and the second part, the f1 and f2, or the u and v as they are traditionally referred to, are quite related. That's why we want to write it at once. So there must exist a matrix. Yeah. So maybe let's write it in words because we are doing this topic for the first time. Write it in words. So f is, sorry, f is real differentiable, or just say differentiable because they've already set it as a function from R2 to R2. So we can just say differentiable because it's already clear. F is differentiable at V if there exists a 2 by 2. And once again, there is literally nothing to remember here because we know that for function from R2 to R, it should be a 1 by 2 matrix, a 1 by 2 row matrix. And in this case, it just becomes 2 by 2 because you're clubbing them together. And the real case also why it was that we motivated because there was two pieces of information we needed to determine the plane and so on and so on. So it's just the sequence that builds up. Okay, so there's really nothing to suddenly having to believe or remember without motivation. In any case, f is differentiable at a point V if there exists a 2 by 2 matrix. Okay, A, B, C, D. Okay, such that this times h, so h is a vector obviously, this modulus divided by this modulus goes to 0. Now, as I was just saying, this is the same as both the parts separately are real differentiable, and that we can just write. This is obviously just equal to, if you just want to see it, it is just equal to, you can break it up. We'll just do this once because maybe the clubbing just happened one shot. So this is just manipulations. You can just break it like this, and then you can break the other part like this, and we get these two things. Hold on, I am making a mistake. This should be comma here. Okay, yes, that should be a comma there, right? And this is something that you can just check. Okay, we just substitute here f1 comma f2. You keep splitting it up, is what you'll get. Now, I mean, if you want this to go to 0, and then what is the modulus? The modulus, so if you call this A and you call this B, right? So you have something like mod of this divided by h goes to 0. But what is the numerator? The numerator is just a square plus b square goes to 0. No, sorry. Yeah, is this something? This goes to 0. Right? Well, but this also means this means that a must go to a by h must go to 0 and b by h must go to 0. Right, because I mean it's greater than, this is greater than a by h, okay, mod obviously. Right, you can check that. Yeah. And also the converse. If a by h goes to 0 and b by h goes to 0, then b by mod h and a by mod h goes to 0, then it's something that you can just check. So that is very simple. So that's why we just club it in one place and write it like this. That's just a notation. So this is the condition. We should be able to guess a matrix here. Well, we don't have to actually guess. These are the partial derivatives. But sometimes you can just know it in other ways. In other ways, this. Now we want to relate. I mean, when I said compare there, I meant comparing the strength of complex and there that we already did. Now we want to formally relate the definitions and see the relation, because then only we can use then only using criteria from real differentiability will make sense in complex differentiability. But now if you take a function from C to C, right? Take a function from C to C. Now let's assume if f is, so here when I say differentiable, or obviously it means complex differentiable. If f is differentiable at z naught, okay, then we know that this limit h tends to 0, f of z naught plus h, f of z naught, and obviously I'm just pulling the derivative this side on the all on one side. So this is just a complex number. This side it was a matrix. This side is just a number. But let's see. Multiply by h divided by h go to 0. These two are different things. Okay. This is a much stronger thing. Okay, this is a much stronger thing because first you divide by h, and here you're first making it a real number and then dividing. So this is a much looser. This will much easily happen. Okay. I mean, obviously, if this happens, right, then you can obviously take the mod and sort of this will also happen. Okay. But before that, one has to understand this carefully. First of all, where is the matrix? This is a function from R2 to R2, right? So f, I mean, it's a function from C to C. Additively, it's a function from R2 to R2. F is ux, let's just maybe say u plus iv. U is a function from R2 to R, and V is a function, the real part and the imaginary part. That's what f is, right? And so basically, this is again a function from R2 to R2. This is a function from R2 to R2. But where is the matrix, right? So what we want to understand, what we want to do maybe is, well, what were we doing? We are corresponding this with u comma v, right? And then in our situation, sorry, in this situation of complex differentiability, the derivative is a complex number. It's not a matrix, right? But how can we view? But and so sorry, what is the complex number doing? The complex number is multiplying with a real number. Oh, sorry, it's multiplying with another complex number, right? How can we capture this multiplication process by a matrix? Okay. So basically what we're trying to understand is how can we understand this as some matrix times h1 comma h2. That's what we're trying to understand. It is again very simple. If this is the derivative, and if this derivative is, let's say, plus ib, and this is h1 plus ih2, then the question is, what should I pick as a matrix so that, and so let's do the multiplication here. You get ah1 minus bh2 plus I times ah2 plus bh1. This, what should I choose as my matrix so that this also comes out to be this comma? So the I is just the second component in this language of R2, so that it comes out to be this. Basically, see, R2 doesn't have a multiplication, right? So that multiplication is worked out by matrices. But matrices turn out to be more general than just multiplication by complex numbers. But yeah, and that means that this matrix will be special. So what should I choose as my matrix here so that we get this? So that is fairly straightforward, right? This is just A and this is minus B. Obviously, there's a more systematic way to get it and so on, just like because this is again a linear map, you can again check its properties and so on and then find it. But it's very easy to just do it by inspection. Okay. Sorry? B and yeah, right. So no, yeah, B. So this should be B, right? Yeah, B and A. Ah, yes, right. So it's very easy to guess also, right? But then we see something very interesting. Now, so let me first remove this. So remember here we are assuming, and that's very important. We are assuming that f is complex differentiable, and then we are seeing how this, what this means in terms of matrices. Okay. If this happens, then this happens, then the matrix ABCD, then the ABCD should be equal to A minus B, B, A. Okay, so let's just see it again, just to recap. F is complex differentiable, then this condition is there. Now we are changing the perspective. And this was because that's what we're trying to do. We're trying to understand it in terms of real differentiability. We are changing the perspective and we're trying to understand it as a function from R2 to R2. So we're viewing it like that. If you view this as a function from R2 to R2, then what does this multiplication become? This multiplication becomes multiplication by this matrix. That means that there is a matrix which is like this, which makes it work. So this ABCD will become this. Yeah, because ABCD was what that unique matrix was. Obviously, that matrix has to be unique, that we know. Must be this. This means that it's special. This already means it's special, right? What does it mean? It means that obviously the B, so that there's no C and D, right? Now, in the real world, what is A? That's right. Yeah, and also relates. Also relates. Yeah, it reduces the amount of variables and also relates the variables. And you will also notice if you just work it out, if you take this, just put some numbers, cos theta, sin theta, you can put maybe, you will see that this matrix rotates numbers. And that's a good old fact that it rotates vectors. If you put in a vector and you multiply it, it will rotate and scale it. And that's a good old fact that complex multiplication rotates numbers. It's a rotation and scaling. Yeah, so it reduces the amount of variable. Maybe that is, I think that's the first thing that one should say. Maybe yeah, so number of variables reduced. But more than that, it means, so once again, we are assuming it's complex differentiable and getting these things. It means that, well, what did A mean before we need to know that? What was A? Obviously, A was was the derivative of f1 with respect to x, or in our situation, the derivative of u with respect to x. Yeah, we agree that is what A is. That is what A is always. That's what we have seen. And so this is A. But then let's write everything. What is B? B is the derivative of u with respect to y. C is the derivative of v with respect to x, and d is the derivative of v with respect to y. This is something that we know. This is universally true. If that is a matrix, then those ABCDs should be this. I mean, we can choose H to be 1, 0, 0, 1. We can get these things. That's how we had seen. So This gives us that if f is complex differentiable, then a must be equal to d, which means that the real part, the partial derivative of the real part with respect to x, very, very strangely, in some sense, should be equal to the partial derivative of the imaginary part with respect to y. That's how it is. This is the condition. It's a necessary condition if f has to be complex differentiable. Oh, so this is just del operator, but it just means partial derivative. It means that just look at u as a function of x and take the derivative. And that obviously you know. I think yeah. You just asked what is this partial derivative. Yeah, sorry. Yeah, yeah. It's called del operator, I think. Anyways, yeah. Not yeah. It's called del. Delta is the triangle. This is del. Okay. So then the other obviously you get. Now this looks very, very surprising. If you don't think about, if one has not thought about complex differentiability at all but just done these manipulations, then this is very surprising. So all we have done right now is just done manipulation. We have just asked the right questions, and then we have tried to relate it with previous things, and we have got this. This is called the Cauchy Riemann equation. So this is the, obviously these things are not surprising. This is not just these manipulations that are giving this result. There are actual mathematical physics from physics, a lot of reasons that can be given why these things hold. But for the time being, it is a consequence like this. Oh, no. I just meant it is new because we started with very basic differentiability of tangents, and then that tangent thing was extended to plane, right, for R2 to R2. So in that sense, R2 to R2 real derivative is not something new. It is just an extension, right? But complex differentiability doesn't have that analog, right? In that sense, I said it is new. And that's why it has very new properties, right? It has like some good functions are not differentiable, not complex differentiable. As you asked, analytic, it suddenly becomes analytic if it is just once differentiable, then it is infinity times differentiable. All these strange things happen, right? So it's a new thing in that sense. Also, there is no clear geometric meaning directly in terms of tangents. So it's in that sense new, and also these variables are tending along complex directions and so on. That's very new in that sense. Not historically new. Historically, no. That's not what I meant. Obviously, historically also it's much more recent than real differentiation. That's also true, obviously. But this is called the Cauchy Riemann equation, and we have not proved anything. We have just derived necessary conditions. This will not help you to decide if something is complex differentiable. No, this will help you to decide when something is not complex differentiable. If they don't, so if there's a function which doesn't satisfy this, then you will say no, then it is obviously not complex differentiable. You can say that, but you cannot decide complex differentiability just from what we have done now till now. Okay, so let us stop here, but just do a very small, simple example and actually verify why this is true. Sorry, I mean verify that this is true in that small example. Okay, and then the next class we will try to get to this condition in a different way, in a slightly different way, and then we will try to see some geometric intuitions as to why it was expected, and then they will show that the converse is also somewhat true, and that converse will help us to decide complex differentiability. So that we'll do next time. But right now, just take a very quick and small example. Okay, so example to verify, just verifying, because this is a little surprising. It's a little surprising if one doesn't think of it a bit. Then it is very surprising. So yeah, example to verify, we can just take fz equal to z square, right? So if you just do this, then you get x square. You can already see that the real part and the imaginary part are always related for a good function, right? When they are not related, when you want to decouple them, when you want to decouple the real and the imaginary parts, then that is when you introduce the conjugates, right? Because then you can just break it up, right? You can just write it in terms of conjugates. Yeah. But then those things which can be decoupled and hence can be written as conjugates will not be differentiable, because conjugate is not differentiable. So it's all tying up. It's all tied up. Okay. Obviously, it's tied up in a more precise way, but just saying. Let's check. So this is the ux comma y. So we can just check. So we just in a carefree way, we just take the derivative with respect to x. You get 2x. Take the derivative of u with respect to u with respect to y. You see, we're just taking the derivative of u. And now take the derivative of v with respect to y. You get 2x. See, these two become equal. We didn't try to make them, we just came out, right? And that's what we already got. So we know that this will always happen for, obviously, this is a differentiable function. So if we knew this even before doing all this. Okay. These functions are also called harmonic functions. They satisfy some other conditions, and there's something called a discrete harmonic function. Basically, these functions are functions which are determined by their values at the boundary, because there is some sort of a rigidity in these functions, and they sort of, what happens at the boundary kind of affects the next point and next point, and sort of there's a rigidity and tension, and so the what happens at the boundary determines everything inside. That is sort of what the idea is behind these things. And one actually quantifies this later on using some theorems. Okay. And there's a discrete version of this also. We will see that maybe later on, next time. Yes. Okay then. Thank you. That's it for today. Thank you.